Okay, can start.
Okay, I think it's recording now. Okay, so yeah, we're gonna have this lecture about statistical method and techniques. I only have like 20 or so slides, so I'm gonna take my time. And you're all welcome to jump in if you have any questions. You can interrupt me, or you can, I will monitor the participants list. If you can raise your hand if that's your style. And yeah, I think as far as other postdocs, there's only Shangyang. So Shangyang, you're welcome to jump in as well if you want to say something at any time. Okay, so let's get started. Just gonna start with some ease, just get the ball rolling, right? With some easy definitions that might be relevant at some point during the talk. So just to review, like we have the axioms of a probability distribution. It says like for all value for which you define a distribution, that probability has to be greater than 0. Like a probability that's negative, it just doesn't make sense. And then the second axiom, there's actually two kind of flavors. If you have a continuous variable, you want that the integral of your distribution is 1. And if it's a discrete variable, then we call this a probability mass function. And then that's just the sum over all possible values of that variable must equal 1. And then there are a few kind of useful quantities that can be defined with these. I just wrote them with, in the case of the probability mass, but it works the same if it's a density. So we have the expected value, which is, it's really just like the weighted sum of the quantities, right? So the weighted mean, it's weighted by the probability, and that's the mean value of the distribution. And then you have the variance, which is really just like the expectation of the square of the deviation of your values from the mean. So that gives you a measure of the spread of the distribution. And then we usually work with standard deviation. It's just the square root of that, and that it's more straightforward for us because it's then the standard deviation has the same units as the expectation and the values that we are measuring. Okay, so let's continue. So our first kind of very important probability distribution will be the, oh, sorry about that, jumping, is the Poisson distribution. And it's a very important distribution that describes the probability of observing k occurrences of an event in a given interval. Like the interval can be time, for instance. It can be distance, anything really. But you got to be able to count the number of occurrences, and the events must occur independently from one another at an average rate that we will just note lambda. And so we have this on the third line. I have the formula, which is kind of fancy. But anyway, just the important thing to know here is that k is an observed quantity. It's a measure, and lambda is a parameter. And then you have, I took this plot of in Wikipedia for various values of parameters, and then each point along this, that's the probability for a given k, so a given number of occurrences. And so one thing to note maybe also is that this is not symmetrical, so this will be important later on. On this slide here, I just want to highlight a very special property of this distribution is that the expected value is equal to the variance. And it's actually just the lambda parameter, so the rate. And so the variance is equal to the mean. And this is extremely useful for us in high energy physics. Because whenever we count something, like in a count, we call this a counting experiment. If, for example, we have a set of triggers or a set of cuts, that we use to select events, and then we just count these events, then the number of events that we actually measure, that will follow a Poisson distribution. And then I think I wrote it explicitly. So if you expect n events after some set of cuts, then on average, when you actually do the experiments, you will observe n events. And the standard deviation of that observed count will be the square root of it. That's useful, for example, in the histogram. That's true in each of the bins. And so if you have an histogram, such as we see here, which is a kind of a measured quantity, and so in all of the bins, the counts that you find in all of the bins follow Poisson distribution. And so you can define error bars here. So that's why it's extremely useful. Okay, so on the next slide here. So whenever we have like an observed count, an observed count, the Poisson uncertainty that we just talked about, like these error bars, they're really just like a fundamental consequence of the randomness of the underlying process. So just mean this is for example, if you think of like nuclear decays, it's a stochastic process, right? It occurs with a certain average rate, and that's related to the half-life. But the time between two different disintegration is not necessarily the same every time. So there's a certain fundamental randomness. And so no matter how clever we are and sophisticated the experiment, if we try to measure like the number of disintegration from a slab of radioactive material in a certain amount of time, then when we repeat the experiment, we don't always get the same count. We get, on average, n with a standard deviation of square root of n, no matter how clever we are. However, there's something to be noted here, is that the relative uncertainty decreases as n grows. And so you take the standard deviation, which is square root of n, you divide by your count, which is n. And then with a bit of math, you can show that this is actually just 1 over square root of n. So this decreases as n grows. And so this gives us like the only recipe to decrease statistical uncertainties is you have to gather more data. That's the only thing that you can do here. And then what about a set of uncertainties, maybe which are unaffected by this n here, by the number of, by our statistics, the number of data that we have? We call these systematic uncertainties. I mean, a classic example would be like the uncertainty due to the smallest units on a measuring stick, for example. But maybe some example in high energy physics would be like, for example, the uncertainty on the electron identification efficiency, and which that for example is very important for anything that's to do with Higgs measurements. We have algorithms that we tune on simulated samples that will, for example, recognize electrons. But there's some uncertainty about how well will these do when we apply them to real LHC data. And so this is a source of systematic uncertainty. You have to calibrate for that, and this introduces uncertainty. There's also like uncertainty on the theoretical models used to make predictions. No matter how much data you have, if that model is super uncertain, then the uncertainty is not going away. These are often modeled with Gaussians. We're going to see that in a bit. And I think maybe if at some point you read Ben's notes, he had a beautiful sentence in there in which he said, let me just pause a second to make sure I get it right. So he says, if you want to decrease statistical uncertainties, wait longer. And if you want to decrease systematic uncertainties, work harder. And I would maybe add, you can work in a more clever way. So for example, if you measure like you want to measure the period on a pendulum, then with a stopwatch, then a source of systematic uncertainties would be like how accurate you can be to start and stop the stopwatch. And no matter how many times you repeat your measurement, this is the same. But if, for example, instead of measuring the time for one period, you just count the time for 10 periods, and then you divide the result by 10, then you just paid the price of your uncertainty one time, but you divided it by 10. So that's a more clever way to work. And it's a way to decrease the systematic uncertainties anyway. Anyways, I'm getting a bit sidetracked here, so let's just move forward. Okay, so I was just talking about the Gaussian distributions. I don't have too much to say on this slide. You probably already have seen this in some way or form at some point in time. So it's also called the normal distribution. In contrary to the Poisson distribution, this distribution has two parameters. So you gotta specify the mean value, which we usually call mu, and this just gives you like the position of the curve along x, as you see on this plot that I also stole from Wikipedia. And there's a variance, which is again just the width of these curves. And so you see curves here with different widths and different values of mu. Again, I mean, I think you all probably hadn't seen this at some point. But why is that important to know? So, for instance, one special property, we see it on the top here, is that since these distributions, this distribution is symmetrical, then just by knowing like what is the variance of the distribution, or what is the standard deviation, you can already know that all the values on average, like they will fall 68% of the time. If a value is sampled from a normal distribution, it will fall within plus or minus 1 standard deviation of the mean. And if you want to know how many will fall within 2 standard deviation, it's 95%. And so just knowing this, it's a very useful factor to interpret results. But even more important is what we call the central limit theorem. And this says that if you have like multiple independent random variables, they don't even have to necessarily follow Gaussian distributions. They're just like random variables. Okay, this is maybe just very technical, but their variance has to be bounded in some way. But anyway, this is true for most useful distributions. So we have this set of different variables. They're all random. They don't necessarily follow the distribution, but the Gaussian distribution. But when you add them together, then the result is approximately normally distributed, at least for large values of n. So let me just state it again, because this is so important. We have many sources of randomness, which are not necessarily normal, but when we add them together, the result is normally distributed. I don't know about you, but I find this absolutely mind-blowing. And this just knowing this means that the Gaussian distribution is often a very good guess. So when you don't know the true distribution to use to model an uncertainty, if it's credible that this uncertainty would arise as a combination of many uncorrelated factors, then a Gaussian distribution is probably a very, very good guess as to the right distribution to use in this case. That's why, for instance, we usually use this to model systematic uncertainties. But I'm going to punt this to later on in the talk once again. So moving forward, so when we have kind of different, we've just talked about like you can sum Gaussian variables, for instance, or non-Gaussian variables, and you will have you'll get some value. But let's explicitly consider now how we can combine uncertainties. So I've just written it here for the simplest possible case, like we have z, which is just like a weighted sum of x and y, which will be, x and y will be our uncertain quantities. So we see that, x has an uncertainty of sigma x, y has sigma y, and there's a covariance, which I've noted here is sigma xy. So the covariance is just how much these two quantities change together. And so if in this case, so we have just the weighted sum here, and then to get the uncertainty, you have to do the sum in quadrature. That's how we call this. So you sum the square of the covariances, and then a term that accounts for the covariance. And let's be even more simple. Let's consider the case where the two sources of variations are independent. So the covariance just vanishes. So we have this formula here, which is like the variance of the resulting variables is like the weighted sum of the two variances. And so maybe one thing that's not fully clear is that why not just add them together, right? I mean, just to me, when I learned this stuff, that's something that I thought would make sense, right? You have, everything these things can vary, and so at an extreme point, why wouldn't we add them? Why do we need to do something like this? And I think, for me at least, the answer lied in thinking of this sort of like the Pythagorean theorem. So if you look at this, the expression for the variance of z, this looks an awful lot like Pythagoras' theorem, right? And so this means that your two sources of variation, since in this case they're completely independent, they're on two different axes. They kind of go in two different directions, and the result is the magnitude of the result will be like the length of the triangle side that you get from having these two variation axes at right angles from one another. And if we go back to the case where we have a covariance, then here, this kind of looks the same, but with a term that accounts for an angle that's not 90 degrees between the two, kind of the two directions. I don't know if that makes sense. I hope it does. To me, these kinds of visualizations help me a lot to understand why this was the right formula. Anyways, as the mathematical expressions of the quantity that you're working with gets more complicated, the formula gets very, very complicated quickly. So in Ben's note, he goes a little bit into detail about how to compute these from first principle by using like Taylor expansions and so on. There's a useful table on Wikipedia. I've even put a link here. And personally, I often end up on that page. So when I just want to quickly check something simple, I usually don't remember by heart all the formulas. But as even with this resource, it gets unwieldy very, very quickly, as you will see once you try to do this. And so this is actually another method to combine uncertainties to do it numerically. And so that's an excerpt actually from Ben's note, where really just wrote some pseudocode where he's actually fitting an histogram with values of PT. So what's the transverse momentum from last week's lecture. And here he tries to model what's the uncertainty and the transverse momentum if the x and y components are uncertain themselves. And so just iteratively, just samples from Gaussian distributions with a certain mean and a certain width, and then adds this together, fills an histogram, and then at the end, once the histogram is filled, you take what's called the RMS. That's the root mean square of the distribution, which is literally the square root of the mean of the square of the deviations from the mean, which is kind of a mouthful. But if you look at the expression right here at the bottom of the slide, you'll see that this is an estimator for the standard deviation of the histogram. And so that's an example of what we call a Monte Carlo technique, which is like a very large family of techniques with which you can compute many quantities by using random numbers in some way. Again, I think in Ben's, oh wait, I hit a button that took me back to the beginning. So let me just navigate back. So yeah, I was saying in Ben's note, he goes into a little more detail about this. So I encourage you to check it out. So let's put this all together here. I've just pulled this figure from the 2012 Higgs discovery paper. So I won't really get into the physics of that plot, since I think next week we'll have a lecture on the Higgs boson. But nevertheless, here we have like the black data points here. That's what was actually measured in the detector. So these are event counts at this is a selection for events with 4 leptons, and we build an invariant mass with the 4 leptons. And in the black dots are what you get from data. These really have a Poisson uncertainty. And in this case, they really made the error bar such that these are a confidence interval that matches the corresponding Poisson distribution. And so that's why you see that they are asymmetric, as we've seen at the beginning of the lecture. But then as the n goes larger, they kind of get more symmetry. The background process prediction, these are the filled histograms in red and purple. These come from simulation, and they are affected by many systematic uncertainties. And so the result of that is Gaussian, since, okay, there's a question in the chat. How do we know that the points follow Poisson uncertainties? Well, that's what we were talking about earlier. Like whenever you have a process where you can model as like you have an interval in which you count something that happens, that events which are independent and are occur at a set rate, like independently of how many of them actually happens. This follows a Poisson distribution. This is just like a very fundamental mathematical fact. I mean, it seems a little weird, right? That if I come back here, that like this really funky formula here would approximate this. But I think, like, I don't have the full answer, but I think this really comes from considering the combinatorics of the problem. And then in the limit where I think your rate is not super large, in practice, this always follows a Poisson distribution. So for instance, if you measure the number of counts that you get from a radioactive material, like you can fit a Poisson distribution and it will fit like extremely well what you observe. And it's the same thing for the event counts. I mean, I think there are very fundamental reasons why we expect that to be the case, but even empirically, we know that this works extremely well. So I hope that answers the question. Let's get back right here. And so, okay, so I was talking about the background processes, for instance, in red, where the systematic uncertainties are a combination of many different factors. And so this is modeled as a Gaussian. You see this, that's like the shaded band. And so data from this channel here, the 4-lepton channel, it's combined with other kind of data to discover the Higgs at a mass of 125 G. And in the remainder of the talk, we're going to consider how exactly is that done. And so it's done using something that we call likelihood. So first of all, I will say that the results of this experiment can be interpreted within what I will call a parameterized statistical model. For instance, in the case of the Higgs, if, for example, I have a set of triggers, I have a set of cuts, And then just from simulations that I did, I expect to have NB background events, that is like everything that's not a Higgs event. And I expect to actually have NS signal events. So that's all the Higgs events. So based on what we just talked about, the right distribution to model this is a Poisson distribution. So when we will do the experiment, we will observe N, that's the count. And so this will follow a Poisson variable with observed count N and with the parameter NS plus NB. All right, that's what over the interval that we're counting the events in, that's how much we expect. So that's just the model part, that's the statistical model. So since before 2012, we didn't know the mass of the Higgs, so we got to account for that. And so we had a first parameter, this is MH. So you see it in the middles. We have this function L, which is the likelihood, and it gained a dependence on the Higgs mass. So here, just I was reviewing these slides before the meeting today, and I thought maybe this is a slightly misleading way to write it, but I just mean that the number of signal events becomes a function of the Higgs mass. So depending on what mass is the Higgs, you don't expect necessarily the same number of signal events. So I said here, L is the likelihood function, and it's a function of the Higgs mass, and it tells us what's the probability that the data that we will observe, what's the probability of that data given some value of the parameters. Another way to say it would be, what's the probability that what we've observed was generated from a Poisson distribution that has these parameters here. It's kind of a measure of how good is a specific hypothesis. And here, by hypothesis, I just mean like a Higgs mass. Okay, the last sentence here, like that's really just a complication that we just won't really get into, but I'm talking here about the case for just one channel in which we count a single number, but we can do this in many channels in parallel, but let's not get into that. Okay, so the likelihood now only tells us about different values of the Higgs mass. But what if there's no Higgs? Or inversely, what if there's more Higgs than we thought? So we usually add a second parameter, which we call the signal strength, mu s. And then you see in the statistical model here, the mu s really just scales. It's the number that scales the number of signal events in our prediction. So with this in place, we can define some useful hypotheses, and hopefully with these hypotheses, the meaning of the signal strength will become clear. So what we call the background only hypothesis, that is no Higgs, that's mu s equals 0. So you see, if you put 0 here, then this terms, the ns term just disappears and we only have background. For the nominal signal hypothesis, that's mu s equals 1. So if we just set it to 1, we regain our previous statistical model, which was just the number of signals plus number of background. Or you can also fit this parameter just to see if it's maybe a value that's greater than 1 would work best. That means there are more Higgs than you even thought. And so that you'll get from the best fit hypothesis. And I will just also say that like these are 3 different hypotheses for mu s, but for the Higgs mass, right? Anytime the signal strength is not 0, then any specific values of the Higgs mass is a specific hypothesis. And then we can test the hypothesis against each other with likelihood ratio tests. That's what we'll talk about right here. So why do we want to do a ratio test? And because the easiest way to frame this is that we need a test statistics that is a single number that quantifies the outcome of the experiment. So that's really like the simplest thing you can say. Just you do the experiment, and then somehow you end up with a single number that summarizes the result of the experiments. So that seems a little abstract, but we'll try to make this clearer. So we have a theorem that's called the name and person lemma that states that the best test statistics that we can have is just take the likelihoods that corresponds to two different hypotheses and just take their ratio. And that's what we have here, the lambda here. We actually call this like the negative log likelihood ratio for a reason we won't get into. But it makes this much easier to work with mathematically. But at its core, it's really just a ratio of the two likelihoods. Here we have the likelihood, which is on top, that's μs equals 1, which is like a hypothesis for a Higgs, the nominal Higgs signal with mass mh. And then the hypothesis I'm testing against is a μs equals 0. So remember that these likelihood, they're Poisson distributions. So we get a count that is n, and then my numerator will be like the value, the probability of that count n if I include the signal, and my denominator will be the probability of that count if I don't include the signal. So this gives me a single number. This number here, well, I made it depend on the Higgs mass because I have not specified it here, and you will see why in a bit. And so we have this single number, but then we have to consider the set of possible numbers we can get from this. There's various ways to estimate this. You can do this numerically with pseudo experiment that is using random numbers to kind of generate under various scenarios what this would look like. I think in high energy physics, we have asymptotic formulas that we use that work quite well. But again, this may be a bit more of an advanced topic, which we won't really get into. But on the next slide, I will attempt to make this a little less abstract. And so you've probably heard of something called a p-value. And a p-value is, for our likelihood ratio test, is the probability that, that based on the test statistic that we wrongly reject a hypothesis. Okay, so remember that we have this test statistics. Here I wrote it Q because the figure I had, they say Q instead of lambda. And so here, if a signal is present, then the likelihood for the signal plus background hypothesis will be greater than that for just the background hypothesis. And so this whole expression here will get like a large negative value. If signal is not present, then it's the reverse. Like the likelihood of just the background is greater, then we only get we just get a large positive value. And so you have the p-value of the signal plus background hypothesis. We really have to ask the question, like, if I assume that, okay, no, actually, let's start with the p-value of just the background only. So if I assume that I don't have any signal, then what is the probability that I get a value of the test statistic that is equal or smaller to what I actually observe? So that's the probability that I'm making an error, right? Because if this is right, I get a positive value. But if this is not right, I get a negative value, or at least something smaller than this. So I want to know what is the probability that what I've observed is actually due to a fluctuation or not.
Wait, so really quick.
Yeah, go ahead.
I'd like to clarify. So if like it says if the signal is present, we get a negative value. So does that mean like if the Higgs boson like exists and the signal like is correct, like that it exists, then there would be a negative value? And then you're saying like,
right. So maybe we can just to clarify this, we can look at the figure, because on the figure you see the probability distribution for the two cases. Okay, so on the left hand side you have FQ given S plus B. So that curve on the left tells you this is the distribution of the test statistics if the Higgs boson exists, okay? So you see that the mean value here is negative. And so on average, this means that on average, right, if the Higgs boson exists, on average, when you make the experiment, you will get a value of the test statistics that is negative. And if you go to the right-hand side, then you have this other curve, which is FQ given B. So that's the background on the hypothesis. And there you see that the mean value is positive. So this tells you that on average, when you do the experiment, if there's no Higgs, your value of the test statistics will be positive.
And the test statistic that you're referring to is the likelihood ratio from the last slide.
Yes, this is the log likelihood.
Okay, so the left one is talking about like the test statistic if the Higgs exists, and then the right one is like if it doesn't exist.
Exactly.
Okay, and okay, yeah, that makes sense. Thank you.
And then actually we can stick with the figure. It's probably easier. You have Q obs, which is the observed value of the test statistic. In this case, we see that just by looking at this, we see that it matches very well the background on the hypothesis, okay? And so now I need to ask myself, what is the probability that, do we want to reject? So based on this, we would reject, right, the signal plus background hypothesis. So we would consider this first p-value here, which is, what is the probability that, given that the signal plus background hypothesis is true, okay? So just consider the case that the right distribution is the one on the left, okay? What's the probability that I have the value Q obs or something bigger than that? And so that's the area under the curve in green, okay? There's very small probability that this Q obs value is actually due to a fluctuation of the signal plus background distribution. And then if we look at the background hypothesis, now I want to know if this is true, what is like the probability that we get this or something smaller? Now we consider smaller just because in that case, it would fluctuate towards the other hypothesis. But in that case, this probability is very large, so we cannot reject this based on this. But I think it's more useful to consider just right the small green area here, which really tells you, in this case, when you have a Q odds like this, it really doesn't match your signal plus background hypothesis here. And the p-value will just be like the probability that that this would be due to a fluctuation. And so if the p-value is under some threshold, you reject the hypothesis. In this case, we wouldn't reject the background on the hypothesis, but we would reject the signal plus background hypothesis. Instead of p-values, you can consider significances instead, which is a useful way to think about this. And this tells you the distance of the observed statistic from the expected value of the given hypothesis. And so in units of standard deviations, that's what we usually say, like n sigma, for instance. And so we reject the hypothesis if the significance of the observation is high.
Wait, sorry, really quick. So you said that with this Q observed, like you would reject the hypothesis of the signal plus background. But isn't the signal plus background like isn't that the correct, isn't it correct that there is the signal plus background?
And in the case of the Higgs, yes. But this is just maybe, I'm sorry if that wasn't clear. This is like a purely synthetic example.
Oh, okay. So this would indicate that the Higgs does not exist.
Yeah, exactly. If that's what we have seen, that would have been a disaster because no Higgs.
Okay, thank you.
because you see like the Q odds is like, it's kind of far away from the expected value of the signal plus background hypothesis. So we see that in this case, it's not the right hypothesis. Okay, I think I have, here we can just actually take that back to the Higgs. It's probably a good time to do this. And so these are example figures where they actually considered 3 different hypotheses for a given mass. So no signal, which is μs equals 0. And they test this against the best fit signal. But I think we also see a curve with just μs set to 1. But we see that they do this hypothesis test for many different values of the Higgs mass. And we see that when we get around 125 GeV, so the p-value gets extremely low. Alternatively, the significance gets very high, which means that what we've observed is actually many standard deviation away from the mean of the background-only hypothesis at that value. So I'm just to make that clear, I'm looking at the middle plot here. So this is what this means. We've done the likelihood ratio tests everywhere along that range, but at 125 GeV, we find that the probability that we observe that value just because of a fluctuation in the background-only hypothesis, that probability is very, very low. And so in this case, we reject the background-only hypothesis. And we accept that we have a Higgs boson. Here it's actually a bit zoomed in. Okay, we are quickly running out of time, so maybe we just, I can just point out that here you see the dashed line, that was like the expectation from simulation, given that the signal strength would be equal to 1 at the corresponding Higgs mass. And you see the shaded band are due to systematic uncertainties. I talk of the look elsewhere effect. I have a slide on this, but I will actually skip it. And if I think just you can click on the link here, which will take you to an XKCD comic. And I'm sure from this comic, you will get what we mean by look elsewhere effect. And it's probably better explained than what I would come up with here. And so the final thing I wanted to talk about was exactly the systematics. I'll just, okay, very quickly. So we have these uncertainties. They're also parameters. Like for example, like what is an uncertainty on the calibration of my electron identification efficiency, for example. That's what we talked about earlier. This is just another parameter, like we don't know the real value of that. And so this enters the likelihood in this way. Like this is very simplified, but now the number of background events in this case depends on the nuisance parameters, which these are just quantities that are uncertain. And so what we do is we profile them away, like just looking at the data, we fit this value to what is most likely given the data. And we say that they're modeled by Gaussian because we include a Gaussian term, which actually constrain the value of these parameters to stay within something that makes sense, right? We get the nominal value and the width, we get this from like auxiliary measurements. Okay. I think this is probably, profiling is quite an advanced topic. I actually had this slide here, which show, maybe we can spend a little bit of time on this slide. Here what we see are, you actually don't see because there's an arrow, but the x-axis here is the signal strength. The signal here is just, it's a Gaussian peak, and there's a polynomial background. And so the parameter is just like how much of the Gaussian are you considering? That's what you see on the top, right? And then you do a likelihood ratio scan of that. You see what's the background hypothesis. These are just the dashed line that you see on the plot. And so you see that in the middle, where these curves are the lowest, if you look at the corresponding histogram on the top, you see here the fit is very, very good. And so this is the most probable value here. But just by scanning on FSIG, you kind of get like a range of values that are probable. On the bottom, though, they've added a nuisance parameter. And so they model the background now as a polynomial instead of just as a constant function. And so for each value of the signal strength, they fit a sixth order polynomial to the background. And so you see correspondingly, this lowers the likelihood, because then in this case, the background only hypothesis matches the data very well also, just not at the peak, but it matches the sidebands much better than in the case where you don't have this. And so this widens the curve and widens the range of possible values of the signal strength. And so that's one consequence of systematic uncertainties. These usually decrease the power of your analysis, because it just makes your background prediction, it can easily adapt to fluctuations in the measured data. So that's just a consequence of that. Here I had put an example with where we actually measure the Higgs mass with the likelihood ratio here. And then they exactly do the same kind of scan of the parameter. Here they scan the Higgs mass. You see the dashed lines are if you don't consider systematic uncertainty, and like the full lines are when you consider them. The different colors are just for different channels, and the black is a combination. But you see in all cases, the curve do actually get a bit wider when you consider systematics, which means that now what you've observed is consistent with slightly more different values of the Higgs mass, which means we are less precise. And okay, here, it's actually just like a different way to look at this. Here they just show like the fit values of the Higgs mass for the different channels. Maybe you can just look at the combine on the bottom. The values within the bracket are the uncertainty that are purely due to the systematic uncertainty. And then the lines are when you add in quadrature, as we've seen, the statistical and systematic components. And so you see that in this case, like the systematic do contribute, but it's clearly dominated by the statistics. And so these sort of measurements will get much better as the DLH gathers more data in the coming years. Okay, I think that's all I had. We've reached the end. I have this short bibliography, which it's basically everything I talked about in this lecture. We have Ben's notes, which is the first link, which I encourage you to read, since it goes into a little bit more detail, for instance, about Monte Carlo method and so on. I think it's totally worth it for you to read this. Okay, at this point, if there are questions, I would be happy to take them.